Okay, then let's talk about the combined events probability, or we also call this probabilities as type of the probability as addition law of the probability. So with this, we need to eventually be able to calculate the various probabilities or multiple events and their intersections, unions, and more, right? So let's talk about the three most commonly used cases. So case one is where we have A intersection B, means when we have event A, event B, there is a chance that these events will overlap each other, right? Then this case is called A intersection and B, and then it can be written as A intersection B. So this is the your symbol for intersection. Okay, and if we are trying to calculate the probability of this, we can write the notation as P of A intersection B, or if we are just trying to calculate the number, we can say N A intersection B. And also, this intersection is same as N in English, so we can write it as A and B, probability of A and B. Okay, then let's look at the case 2. So the event that both A or B or both occur, so they are inclusive, they're affecting each other, right? So we have a case where they are inclusive of each other. Then in this case, if we are representing this case with the Venn diagram, we are representing case where we have event A and B, and they are inclusive each other. So we are just talking about everything in there. Okay. So in that case, we have to use the notation union. So it can be written with the symbol U, B, and if we're trying to calculate the probability, we can say probability of A union B, or if we're just trying to calculate the number of the samples within these events, we can say N of A union B, or since the union U represents the OR in English, we can rewrite it as P A or B. Okay, and also there are formula that we can calculate this case. For this, we can use probability of A union B is same as probability of A plus probability of B, and since we are adding two events that occur in same time, there can be a overlapping part, right, which is this part, or it can be identified as P A intersection B. So we have to subtract that extra intersecting part. So this is the formula that you can use to calculate the union when it's on inclusive events. Okay, then let's talk about the last case today. So this case is the mutually exclusive case where A and B are disjointed. So event A and B are disjointed. So however, mutually exclusive case is very similar to the independent events. However, they are also little different. Okay, so when you have a mutually exclusive case, we are actually referring to the case they are not inclusive, means they have nothing to do with each other. So they are simply, we can say that if A occurs, if A happens, B cannot happen. Cannot occur. Okay, so that's mutually exclusive case. They're not inclusive either. So to have a mutually exclusive case, they cannot occur at the same time. And should be no intersection. So this is the part where it is very similar to the independent case. However, they use the OR events. Means they're using the A union B. Okay, so because of that, they're using the addition rule. So since they have no intersection, we know that P A intersection B is 0, right? However, they're using the addition rule or the A union B, so we have to use the we can still use the P A union B formula to calculate the mutually exclusive cases. However, it is equal to PA plus BB only, because we know that PA intersection B is equal to 0, right? So to calculate the P of A union B of the mutually exclusive events, we need to use the PA union B equals PA plus PB. Okay? Then let's talk about the independent and dependent events. So first of all, independent events is quite interesting. It is pretty similar to the mutually exclusive events, however, they are different. So when we have independent events, the events that happens during the time actually can happen in same time, right? But if you remember about the mutually exclusive case, they cannot occur in the same time, right? So we have independent events if the events occur at the same time, and however, they also can have intersection in the independent cases. Okay, they can have it. And in this case, they are actually doing n events. They also use the multiplication rule to calculate their values. Okay, so if event A and B are independent events, then we can say that PA intersection B is same as PA times PB. Okay, and this rule can also be extended for any number of the independent events. Means, so if there are events A, B, and C, and if they are independent events, then we can also say PA intersect B intersect C is same as PA times PB times PC. Okay, then let's try example number 4. So we have a coin and a die, and they have been tossed and rolled simultaneously. We need to determine the probability of getting a head and a 3 without using a grid. So means this coin and die, these events does not affect each other at all, right? And they're happening simultaneously. That means this is an independent case. So we need to find the chance or the probability where head is intersecting the 3, right? So the probability of getting head from a coin is 1/2. The probability of getting 3 from a die is 1/6. So since we need to calculate the probability of head intersecting 3 for an independent case, we have to do probability of H times probability of 3. So the answer is 1/2 times 1/6, which is 1/12. Okay, so that was independent events. So now let's talk about dependent events. So two or more events are dependent if the occurrence of the one of the independent does affect the occurrence of the other event. Therefore, when an experiment involves sampling, it is possible to conclude that without replacement, we can have the dependent events, with the replacement, we have independent events. So in case the events A and B are dependent events, then we can say that P of A intersect B can happen when P of A multiplies to P of B given that A has occurred. Okay, so let's try to apply this formula into a case so we have a better understanding of the formula. So example number 5, we have a box contains 4 red, 2 yellow tickets. 2 tickets are randomly selected from the box one by one without the replacement. Find the probability that both are red, and B, the first is red and the second is the yellow, right? So without replacement means we have dependent events. So this identifies this event as dependent case. And we have a box that contains 4 red tickets and 2 yellow tickets. Okay, so question A, we need to find the case where both are red. So means we need to find the probability that first is red intersecting the second is also red. Okay, so we need to find the, using the formula, we're going to write out the formula first. Okay, so we need to then this is same as probability that first is red times probability that second is red given that the first is red. So means the first one, the probability of first is red is same as 4. There's 4 red tickets, right? And there are 6 tickets in total. So we do 4 over 6 times second is red given that the first is red, right? So we are doing this without replacement, but that means after first pick, the number of the red ticket has decreased to 3, and also the number of the total ticket has decreased to 5, right? So the probability that both are red is equal to 12 over 30 or 2 over 5. Then question B, we need to find the probability that the first is red and the second is yellow. So what we need to do is we need to find the probability that first is red intersect second is yellow. Okay, so we're going to do just like question A, we're going to set up the equation first because this is our first time doing this. So we need to find the probability that the first is red times probability is that second is yellow given that the first is yellow, the red. Okay, so probability that first picked ticket is red is 4 over 6. And the probability that second ticket is yellow given that the first is red means we still have two yellow tickets left, so it's 2 over. However, since we already picked one ticket out of this box, the total number of tickets left in this box is 5, so we do 2 over 5. So the total number of the ticket is 8 over 30 or 4 over 15. So let's now talk about the conditional probability. So when we were talking about the dependent events, we already talked about A occurs given that another event already occurred, right? So that part is called the conditional probability. We can identify the conditional probability with the notation A bar B to represent the event A given that B has occurred. And we can calculate this P of A bar B using formula P A intersect B over PB, or we can also just use the number of the samples in an event, means N A intersect B over NB. Okay, then let's try to apply this formula into an actual case. So here, example number 6, we need to find PA bar B if the question A, the if probability of A intersect B equals 0.1 and PB is equal to 0.4. So question A, we have to find the PA bar, right? PA bar, according to formula, is same as PA intersect B over PB. So we can say this is same as 0.1 over 0.4, which is equal to 1.4. Question B, we know that PA value is equal to 0.3, P of B value is equal to 0.4, and also we know that P of A union B is 0.5, right? And now we need to find the probability of A given that B has occurred already. In order to do this, we still have to use the same formula, PA intersect B over PB, but we first have to identify the P intersect B, right? And we know the P of A union B value already. So let's just use P A union B is equal to P A plus PB minus P A intersect B value formula. Then we can say that P A intersect B is same as PA plus PB minus PA union B. So this is same as 0.3 plus 0.4 minus 0.5, which is equals to 0.2. Then we can say that PA bar B is same as PA intersect B over PB, and we know that P intersect B is same as 0.2 over PB is same as 0.4. So this is equal to 1 over 2. So we have found our answer. Then question C, we have events A and B that are mutually exclusive. So when you have a mutually exclusive case, there's no intersecting part. So it means PA intersect B is equal to 0. So that means PA bar B for mutually exclusive case is 0. Then now let's try to apply this concept into the real life situation. So we have a here with the example 7, in a group of the 60 students, 40 studies mathematics, 32 studies arts, and each student studies at least one of these subjects. So we first have to identify the Venn diagram to find how many students study both subjects. So question A. So let's say we have math and art like this, and I'm going to say this is art and this is mathematics M, and the total number of M union A is equal to 60, and the number of mass is 40. The number of the samples in art is 32. Number of the arts is 32. Then using this formula, these variables with the formula N A union B is equal to NA plus NB minus NA intersect B, we can find that intersecting value, right? So we have 60 here, 40 plus 32, 32 minus NA intersect B, Then from here, we know that we have NA intersect B equals to 40 plus 32 minus 60, which is equal to 12. So we have 12 that's intersecting. So M intersect A. That means we have 28 for mathematics, or the student who's only taking mathematics, and we have 20 students who's only taking art, right? Then we can say question A, 12 students study both subjects. Then question B, if a student from this group is randomly selected, we need to find the probability that he or she studies mathematics but not arts, right? So we are talking about this portion. So to find the probability, we just have to do 28 means number of the students who's only taking mathematics over total number of the students. So the simplest form of this fraction is 7 over 15, and this is your answer. Then question II, we need to find the probability that this student studies art given that he or she also studies mathematics, right? So we have to do probability of arts given that these students also studies mathematics. So mathematics, okay. So we can do the probability of the art intersecting mathematics over probability of student only taking mathematics. So we can, this is equals to 12 over 40. So the final answer is 3 over 10. So let's go over some of the IB questions. So here we have a question from year 2016, paper 2, and it is from November examination. So we have a group of 66 people went on a holiday trip to Hawaii. During their stay, 3 trips were arranged: a boat trip B, coach trip C, and helicopter trip H. From this group of the people, we need to identify all these informations. Okay, so question A, we have to draw a Venn diagram to represent the given information using the sets labeled BCH. Okay, so let's say we have a B, C, and H with a sample space U. Okay, so this is sample space U, and I'm going to say this is our B, C, and H. And then let's move this information into this Venn diagram. So first information we have is 3 went on all 3 trips. So 3 goes here. And 16 went on a coach trip only. So that means here. And 13 went on the boat trip only. So means this number goes here. And the 5 went on a helicopter trip only. So means 5 goes here. And X number of the people went on a coach trip and the helicopter trip, but not the boat trip. So means we have X amount of people who did this much of trip, and we also have 2X went on a boat trip and helicopter trip, but not the coach one. So 2X goes here, and 4x goes to here because they went on a boat trip and coach, but not the helicopter one. And 8 people did not go on any of the trips, so 8 goes here. Okay, so that was question A. So let's label this as A. Then question B, we need to show that x is equal to 3, right? So we all know that when we add all these values, they should add up to 66, right? So we can say, so 13 plus 2x plus 3 plus 4x plus 16 plus x plus 5 plus 8 is equal to 66. So what I did is I just added all the numbers of the samples, right? And we can now solve for the x value. Then we have 7x plus 45 equals 66, right? So 6x, 7x. And then we can solve for this x value, which is 66 minus 45. And then 7x is equal to 21. X is equal to 3. Okay? That's how you solve the question B. Question C, we need to write down the value of the n or b intersecting C, right? So n or b intersecting C is same as 4x plus 3. The reason why I'm saying this is we are trying to find the parts where b is intersecting C, right? So we are actually looking for this part here. Okay, so that's the reason why it is 4x plus 3. Then we since we know the x value as a 3 from the question B, we can simply substitute 3 into the x. Then we get 15. Then n or b intersect C is equal to 15. Then let's talk about question D, I. So we need to find the probability that this person went on at most one trip. Means this person can go into no trips. So probability that this person can go into no trips. And we also have to find where this person went on at least one trip, right? At most one trip. So going only one trip. So we know that the probability that this person didn't went on any trip is 8 over 66, right? We have this information here. And then this at least this person went on once is referring to this part, and this part here. So we can say 5 plus 13 plus 16 over 66. So this is equal to 42 over 66. Then you need to simplify this fraction, right? So this becomes 21 over 33, which is equal to 7 over 11. Okay, that's the answer. Question D, II. So we need to find the probability that this person went on a coach trip, given that this person also went on both the helicopter trip and the boat trip, right? So we need to find the probability that this person went on a coach and then the helicopter trip and the boat trip. So we need to find the case B intersect H. Then this can be rewritten as P C intersecting B intersecting H over probability that B intersecting H. Okay, so this is same as 3 over B intersecting H is referring to this part here, 2x plus 3. So we have to do 2 times 3 plus 3, right? Because x is 3. Then we can say 3 over 9, which is equal to 1 over 3.